All right, so welcome to the next installment of irradiation. Went through some basic stuff last class. Going to get a bit more into the details, nitty-gritty, harder questions to deal with radiation. So first up, we've mainly been dealing with black bodies, so emissivity, absorptivity, both equal to 1. Obviously, that's not always the case. In general, radiation hits a surface. Some of it's going to get reflected. Some of it is going to get absorbed. Some of it may get transmitted, but we're going to ignore that for now. We're only going to be dealing with reflection and absorption. That's all that's going to happen. So whatever does not get absorbed is going to be reflected, and that's it. Now, when these reflections happen, interesting things happen, or interesting things can happen. That reflection can either take that energy out of the system completely, or it can reflect it back onto something else in the system. So for example, if I have two objects interacting with each other, object number 1 emits some radiation, it then hits object number 2. Some of that, it gets absorbed into object number 2, but some of it gets reflected. And this reflection can, just like emission, can happen in all directions. And so that reflection, some of it goes off into space, some of it comes back and hits that object 1, and then we can have object 1 who's absorbing some of his own radiation that he initially emitted and got reflected off the other surface. So sometimes that becomes, or can lead to some fairly complicated scenarios. We'll see how to deal with those later. To make the situation at least somewhat doable, I want to make some assumptions. And so we're going to assume that all surfaces are uniform in temperature, so same temperature everywhere, so same amount of radiation coming off each part of the surface, assuming everything's, again, being radiated equally in all directions. No energy is being transmitted, like I said before. It's only either absorbed or reflected. And these reflective and emissive or absorptive properties, including something called irradiation and radiosity, which we're going to define in about a minute, less than a minute probably. Those guys are also constant over the entire surface, so that it's, again, same amount coming from every part of the body. So irradiation, capital G, that is the total radiation hitting the surface. So from all other sources, all these other things are radiating thermal radiation, and that's whatever hits this object is its irradiation. So total energy hitting my object, capital G, is irradiation. Per unit time, per unit area. Radiosity, kind of the opposite, is the total amount of energy coming off of a surface, per unit time, per unit area. And so the radiosity can come from two sources. It can come from the object itself. So the object itself is at some temperature. That temperature causes some thermal radiation, sigma T to the 4th. So there's some epsilon times EB. EB, remember, just sigma T to the 4th. So that's the energy coming off the surface due to the surface itself at some temperature. Then there's also part of this radiosity that gets reflected from the irradiation. So some of this G gets absorbed, some of it gets reflected. The part that gets reflected, rho G, is part of the radiosity, because radiosity is the total energy coming off the surface. So if you look at this, again, radiosity, I have epsilon EB plus rho times G. And then rho, because things can only be absorbed or emitted, the reflectivity is 1 minus alpha, the absorptivity, but absorptivity is the same as emissivity. So rho is 1 minus epsilon. So I can write this all in terms of just epsilon. Epsilon EB plus 1 minus E times G. You can also rearrange this, solve for G essentially. So move that to the other side, divide by 1 minus epsilon. Capital G is capital J over 1 minus epsilon EB over 1 minus epsilon. Then if you look at the net energy leaving the surface per unit area, so J is leaving, G is coming in, net out minus in, J minus G. So J minus that G, and we can replace the equation we had before. And then these two terms both involve a J, so I can combine them. So basically put this common denominator, 1 minus epsilon on top, expand it out, things cancel. I'm left with epsilon EB over 1 minus epsilon minus epsilon J over 1 minus epsilon. solving this for Q, so multiply by A, and pull out the epsilon over 1 minus epsilon. I have epsilon A over 1 minus epsilon, EB minus J. Or the better way to write this, as we'll see later, is basically flip this upside down in the numerator, in the denominator. And so I have EB minus J over 1 minus epsilon over epsilon A. So any surface, the total energy coming off that surface is given by this formula here. Now the reason I like it in this form is because it kind of matches what we did way back in the first few weeks of class when we dealt with conduction through multiple layers. I had a total resistance on the bottom, and so this is kind of the same thing. I don't necessarily have total temperature or temperature difference on top because it's radiation, it's T to the fourth, it's not quite the same thing. But then again, these EBs are like sigma T to the fourth, so it's kind of like that's my driving force, and then the bottom is like my resistance, so I can see what the resistance is for this scenario. This resistance basically comes from the fact that not all the energy leaves the surface. There's this epsilon involved, and so because not all the energy is leaving the surface, there's a resistance associated with that. Not all of it makes it out. So that's just for the object itself. Now, once that radiation actually leaves the surface, it has to go and interact with another object. And so if I have some energy leaving the surface per unit area, it has to then go and actually hit the second surface. So the total amount of radiation that leaves surface 1 and reaches surface 2 is J1A1 times F12. So again, total energy per unit area times the area times that shape factor, how much of it actually hits object 2. I can then look at what's going the other way. So what leaves surface 2 and hits surface 1, and then the net interchange is just the difference of those two things. So Q between 1 and 2 is the energy from 1 hitting 2 minus the energy from 2 hitting 1. And so Q12, J1, A1, F12 minus J2, A2, F21. And then A1, F12 is the same thing as A2, F21. Saw that last class with the shape factors. And so we can pull that out. So J1 minus J2 is A1, F12, or it's J1 minus J2 times A2, F21. Generally, whichever one's easier to calculate in terms of the shape factor is usually the one you go with, because they're both the same. Again, here I can write this in terms of the total driving force, in this case J1 minus J2, over the total resistance, in this case 1 over A1 F12, or 1 over A2 F21, again, same thing. But again, I can see here I have this resistance. So this resistance basically, again, due to the fact that not all the energy leaving surface 1 is going to hit surface 2, and so that's the resistance associated with that. That's really what we have for these two objects that are interacting with each other and nothing else. My overall heat transfer, difference in my EBs, so sigma T to the fourth for object 1 minus sigma T to the fourth for object 2. And then I basically have three resistances. I have the resistance of making it off surface 1. I have the resistance of actually making it to surface 2. And then I have the resistance of that surface 2 actually absorbing this radiation. So again, this is similar to what we did for conduction through multiple layers, or maybe in this case it's more appropriate to call it convection on one side, conduction through the surface, and convection on the other side. But again, total resistance for two objects, you need to make it off the surface, you need to make it to the second object, you need to make it into that second surface. A good way to keep track of this is to set up a radiation network. So then this is just like the equivalent circuit diagrams we drew before. So I have some object 1 at some temperature or energy EV1, some resistance to make it off that surface. That gets me to what we call J1. So actually leaving the surface. J1 has to make it to J2, so has to make it to the second object through some shape factor relationship. And then once it gets to J2, it has to be absorbed into object 2. So I have to go from J2 to EB2 through this resistance, 1 minus epsilon 2 over epsilon 2 A2. So you can see from this, I have a nice series circuit. Series circuit, just add the three resistances together. So my total resistance, 1 minus epsilon 1 over epsilon 1 A1, plus 1 over A1 F12 plus 1 minus epsilon 2 over epsilon 2 A2. That's my total resistance. So Q12, which is EB1 minus EB2, or sigma T1 to the fourth minus T2 to the fourth over this R total, which is just the same equation we had before. I just had this all written out instead of just calling it R total, had this big ugly mess on the bottom, but end up with the same equation. So that is for two objects interacting with each other, nothing else. It gets really fun when we have more than two objects. For example, three objects. So three objects, I can have object 1 interacting with object 2. It's also going to interact with object 3. Then object 2 and 3 can interact. So I have this kind of triangular resistance network. So usually these are set up as these triangles. So I have very similar resistances. So each of these orange resistances represents the surface, so getting from the inside of the object at EB1 to actually coming off the surface, J1. Same thing for EB2 and J2, same thing for EB3 and J3. This orange line resistance is going to look like 1 minus, in this case, epsilon 3 over epsilon 3 A3. So whichever one I'm going through has a resistance that looks like that. Then once I'm at the J's, for the J's to interact with other J's, those are all done through shape factors. So J1 has to have some of its energy go to J3, some of its energy goes to J2, and that's given by these 1 over A1 F12 or 1 over A1 F13, whichever two things are interacting. Those are my green line resistances through those networks. To solve this system, generally what you have to do is look at the equation at each node. So at each node, for example, this node 1 right here, whatever energy comes in has to equal whatever energy comes out, just simple energy balance or conservation of energy. And so if I look at this node 1, simple conservation of energy gives me EB1 minus J1 over that resistance. So this is basically coming in this line. J2 minus J1 over 1 minus A1 F12. That is this green line up here. And J3 minus J1 over 1 over A1 F13. That's this line here. So again, the way I've set this up is I've basically said everything is going either into or out of J1. So I have J1 at the end of each of these. So basically said everything's coming in, has to all add up to 0. So all three things come in, adds up to 0. You can look at it as stuff coming in, stuff coming out. Then have stuff coming in on one side equals stuff going out on the other side. The problem with coming in, coming out, you have to really worry about which way these things go. So I basically had to pick a direction. I'm saying to the right is the way things are going. So EB1 would be coming in, J2 would be going out, J3 would be going out. They have to worry about is it J3 minus J1 or is it J1 minus J3? So that's why I like doing it this way, because if I take just everything goes into or out of J1, then J1 is either second in all of these or J1 is first in all of them. It doesn't actually matter because that's just multiplying by -1, and 0 times -1 doesn't change anything. So I can either have the way I have it written, or I can have J1 minus EB1, J1 minus J2, J1 minus J3, all adds up to 0. So that's the way I do it. Before I go on to the next one, so that's just for node 1. I can write a similar equation for node 2 and a similar equation for node 3. That's going to give me a grand total of 3 equations. And I have 3 unknowns. My 3 unknowns are my J values, J1, J2, and J3. So generally the way I solve this big ugly mess is to have 3 equations, 3 unknowns, solve for my J's. And then once I solve for my J's, I can solve for any sort of heat transfer, heat loss or gain by any object, because that's basically EB1 is going to lose energy through this orange line. So any energy lost is going to be equal to EB1 minus J1 over that resistance, 1 minus epsilon 1 over epsilon 1 A1. I do the same thing for object 2 or object 3. One way that these networks become easier is if an object is insulated. If an object's perfectly insulated, or if it's perfectly reflective, that also works as well. It's going to re-radiate all the energy incident upon it, so nothing gets absorbed in those cases. Everything basically gets reflected. That gives us 0 heat flow. So I have 0 heat flow up this line, so I basically just take it out. And once I take that out, the J there equals the EB there. So in this case, I've looked at object 1 as being the insulated object or perfectly reflecting object. And my radiation network becomes this guy here, which is actually easier because I generally know what EV1 is. That's just sigma T1 to the 4th power. So that guy is no longer an unknown. And all I have in this case is 2 unknowns, J2 and J3. So I generally still have 2 equations and 2 unknowns, but that's a lot better than 3 equations and 3 unknowns. So my life gets a lot easier in this case. Another way this happens is if I have a very large surface. A very large surface has a very large area. If we look at the resistance in terms of these orange lines, resistance is 1 minus epsilon over epsilon times A. If A is very large, then this whole thing is essentially 0. If I have 0 resistance, 0 resistance means nothing's lost, so J1 equals EV1 in that case as well. So very similar case, whether it's insulated or very, very large, I end up with this diagram looks like this. Again, this is assuming that object 1 is the one that has the special condition. Again, it makes my life a lot easier. So a couple examples. First example we're going to do involves the exact same situation we had last class. So we had this example last class that I have this wall or this room that's 4 meters by 4 meters by 3 meters tall. One side maintained at 260 Celsius, floor maintained at 90. And I just basically last class calculated the heat transfer between those 2 objects. I pretty much ignored the other 4 surfaces, the other 3 walls and the ceiling, which was not entirely correct. Generally those guys are there and they're going to do something. But to know what they're going to do, I need to know something about them. So this time I'm going to add in the fact that the other 4 walls, technically 3 walls in the ceiling, are perfectly insulated. I want to calculate the net heat transfer between the wall and the floor in this case. I'm going to assume all surfaces are black, so epsilon equals 1 for all surfaces. So same scenario as last class, so we have the same values. EV2, sigma T2 to the 4th, is 5.67 times 10 to the negative 8 watts per meter squared, Kelvin to the 4th power. My floor, the wall is at 260 Celsius. So turn that into kelvins and to 4th power. Gives me 4,576 watts per square meter. Can we do that last class? Same thing for the other. In this case, the floor, 984 watts per square meter. Got that from last class. Shape factors, again, same as last class. F12 is 0.18. Area 1, so my floor is 16 square meters, 4 by 4. Area 2, my wall, 12 square meters, 3 meters by 4 meters. So since my room's completely enclosed and due to symmetry, so basically any radiation coming off of surface 1 is either going to hit surface 2 or it's going to hit the rest of the room, which I'm going to call surface 3. So basically the energy from surface 1 has to go somewhere. 18% of it hits, which ones are object 1 and object 2? Object 2 is the wall. So 18% of the stuff coming off the floor hits the wall. The rest of it is going to have to hit the rest of the room. So 82% essentially hits the rest of the room. So F13 between the floor and the rest of the room is 0.82. And then I still want to do the same thing for F23. I'm going to need that in my radiation network. So I can do that by doing 1 minus F21. So again, same thing. All the radiation coming off of surface 2, some of it hits surface 1. The rest of it is going to have to hit surface 3, I mean. And so whatever does not hit surface 1 is hitting surface 3. So F23 is 1 minus F21. F21 I can calculate because that's A1 over A2 times F12. So A1 F12 equals A2 F21. And so that, it gives me 0.76. And then my junction diagram, object 3, my wall, or my rest of my room, is what I'm assuming to be insulated, so that guy doesn't have a branch on him. J3 is just EV3, EV2, and EV1. Because all surfaces are black, epsilon is 1, so 1 minus epsilon 2 gives me a 0, so no resistance for this guy. Same down here, no resistance for that guy. So J1 is just EB1, J2 is EB2. Then I have these shape factor resistances, 1 over A1 F13 between 1 and 3, 1 over A1 F12 between 1 and 2, same thing between 2 and 3. And I get my total resistance, or total heat transfer, Q sigma T to the fourth, so T1 to the fourth minus T2 to the fourth over the total resistance. Total resistance in this case, so basically going from object 1 to object 2, get no resistance down these orange lines. So I have two options. I can either take the direct route from 1 to 2, which has a resistance of 1 over A1 F12, which I can calculate to be 0.347, or I can take the long route. I have to go through A1 F13 and A2 F23. So both of those resistances, 0.076 for the first one, 0.110 for the second one. So basically I have a parallel option. I can take this one, 0.347, or I can take this one, whose total is 0.076 and 0.110. So that's basically what I have here in ugly calculated variable form. But basically it's just, I have the option of my first one or the second one. So basically this would be 0.347, and then this would be those two guys added together. Grand total of that is 0.121 for my total resistance. And so either ugly number form or easier form, EB2 was 4576, EB1 984, total resistance 121, gives me 29,670 watts for that guy. Second example, I have two parallel discs, each 50 centimeters in diameter, separated by a distance of 12.5 centimeters, enclosed by a large room at 300 kelvins. One disc maintained at 800 Celsius, epsilon value of 0.8, other disc perfectly insulated. I want to know the energy lost by the first disc, the one at 800 degrees Celsius. So for this, I'm going to need to know my shape factors. So it's very similar, again, to what we did last class. There's an example using two discs. Figure 13.5 or table 13.2, there's an equation. I can get F12 is 0.61. Notice in this case that the two discs are both 50 centimeters in diameter. So because of that, they're the same area. Because they're the same area, A1 F12 equals A2 F21. Area is the same. So F12 and F21 are both 0.61 in this case. Also, just like the last example, a very large room that's basically around both discs. So the discs are either going to hit each other or they're going to hit the rest of the room. Whatever they don't hit from each other is the rest of the room. So F13 is 0.39, 1 minus F12. And same thing for F23 because F21 is also 0.61. So F23 is 1 minus F21. So same number for that. In terms of the radiation network, again, it's going to look very similar to what we had before, just slightly different numbering, because now what I'm going to call object 2 is disk 2, and that's the one that's insulated. Object 1 is the disk at 800 Celsius. Object 3 is the surrounding room. I still need my EBs, so sigma T to the fourth for object 1. It's at 800 Celsius, so I want to make sure that's in Kelvin, times 5.67 times 10 to the negative 8. Gives me 75,000. The room was at 300 Kelvin, so that is already in Kelvin. That to the fourth power times 5.67 times 10 to the negative 8 gives me 459 watts per square meter. Then again, here's my network. The room itself, if you remember, in the question said it was large. It's a large room. So anytime I have a large room, have a large area. Large area means zero resistance. So EB3 and J3 are, again, essentially the same thing, no resistance through this line. But I do have a resistance in this one for my disk, as well as a resistance from the shape factors. So calculating all of those, for my disk, epsilon is 0.8, area pi r squared, pi times 0.25 meters squared. It gives me a resistance 1 minus epsilon 1 over epsilon 1 A1 of 1.27 for this orange line down here. A1 F12, shape factor between the two disks. So 1 over pi r squared. shape factor was 0.61, so that gives me 8.35 between my two disks, object 1 and object 2. And then between the disk and the wall, or the room, 1 over A1 F13, again, area pi r squared, pi times 0.25 meters squared. F13 in this case was 0.39, so 13.1 resistance between my first disk and the rest of the room. Then because, again, all the properties for the first disk is the same as the second disk, so I'm also going to have the same resistance between the second disk and the room itself. So I'm going to replace all these with their numerical values. So 1.27 down here, 8.35 between the two disks, and 13.1 between the wall and the disks. Then in terms of my total heat loss from my first disk, so the heat loss from the first disk is basically only has the option of going to the wall or the rooms. None of it is going to go to the second disk. I mean, it's going to go there, but it's not going to be absorbed by the second disk. Second disk is just going to kind of reflect it away. So none of the energy leaving object 1 is absorbed by object 2. So all the energy that's lost from object 1 goes into object 3. So that's why when I calculate the energy lost from object 1, I want to look at what goes to EV3. So I'm kind of going all the way from EV1 to EV3. Again, that should technically be T2, T3 to the 4th power. And then my total resistance, 1.27, so I have to go through that, 1.27. And then I have an option. I can either go through this 13.1, or I can go through 8.35 plus 13.1. So the parallel stream there, written out better than I had in the last example. It's actually just numbers. You can see option number 1, 1 over 13.1. Option number 2, a total of 8.35 and 13.1. Parallel to 1 over all that stuff. Gives me grand total resistance of 9.4. Then EV1 we found was 75,000. EV2 was 459. So total heat loss from object 1, 7,947 watts. So that is more complicated radiation, specifically interaction between 2 or 3 objects. We're going to see a few other simplifications and simple scenarios of this, and then go on to more complicated ones after that.